Hi, welcome to the video lecture for week 2. We're doing this by video because week 2 of the fall semester is Labor Day, and so we're not having class tonight. But I wanted to give you something to think about this week. What we're going to think about and work on in this video is the concept of what's called maximum likelihood estimation. So if you've never heard of that, that's okay, but hopefully you'll come to know that this is something that is quite a good technique, particularly in modeling of many situations in psychological science, especially in cognition, which I'm most familiar with. But it's a general technique that's been around for a long time. So let's jump into it. Now, to understand what maximum likelihood estimation is, we need to go back to what we talked about in week 1, which was the concept of a probability function. So if you remember from that week 1 lecture, we talked about the definition of a probability function. And we gave a few examples. And one that we spent some time working on was the notion of the binomial distribution or the binomial probability function. So if you'll remember from that lecture, and you can go back and look at your lecture notes to see this as well, the binomial distribution is a function that models the probability of getting a certain number of successes when you have a fixed number of independent, what are called Bernoulli trials. You can think of Bernoulli trials as being coin flips. They're essentially trials on which there's only 2 outcomes, kind of like heads or tails, and there's a fixed probability of getting what we call a success on any one of those trials. So anytime you can think of a situation as being n independent coin flips, with each coin flip having a fixed probability of landing heads, then you've got a binomial distribution. Now, the probability function for that binomial distribution is given by this formula in the middle. And the way this formula is read is f of x given theta equals all of this stuff. And we talked about this formula last time, and that's not too important for this lecture. But what is important is this little expression on the left, f of x given theta. So essentially, x is your data, and you're given a parameter. You're given a value for theta. And so you want to know what is the probability of this data, x, given a certain parameter. Now, we've done this already. We did this last week. Particularly, we were able to construct a graph or a bar plot of the probability distribution. We can do so in R with some coding here. We're actually going to demonstrate this in a second. To give ourselves a fixed situation to deal with, let's suppose that we're dealing with the case where you have n equals 20 trials, and we have a fixed parameter of theta equals 0.7. So on each of these 20 trials, the probability of landing heads is 0.7 or 70%. And so now we can plot the probability distribution. So I'm just going to copy this. And by the way, all of these commands are available on the GitHub site. It's week2.r. Okay? If you just open that up in RStudio, you'll actually be able to have all these commands already. But I'm going to copy this and put it directly into RStudio for us. And then I'll just execute this. Remember, to execute a command from RStudio, you write something in the script editor, and then when you hit Control-Enter or Shift-Enter, depending on whether you're using a Mac or a PC, sorry, not Shift-Enter, Control-Enter or Command-Enter, then you will see the output put over here in the console. So we'll do a little Command-Enter here. And right down here at the bottom, we get a graph of the probability distribution. Now, what this graph represents is the probability of getting each possible number of heads in those 20 outcomes. And you'll see the most probable occurrence is somewhere after 13. So this is probably 14. I've got a little bit better graph on the slide. We can go back to that. You can see the most probable outcome is 14 heads, which of course makes sense. If the probability is 70%, you can expect on average 70% of 20 to come up heads. So that's what this probability function tells you. It tells you the probability of each discrete outcome. Now, as I just said, the probability function, the form is important. When you say f of x given theta, this is telling you the probability of data given a parameter. Okay? Probability of data given a parameter. What happens if we switch these? What if we wrote this function, well, I've changed nothing on the right-hand side, but I have changed the left-hand side. What if I change this to the probability of a parameter given data? Okay, and what this turns into, the formula stays the same, but what this now turns into is that the inputs, instead of being data, are now parameters. And this is what's called a likelihood function. It is different from a probability function. To see why, let's look at an example. So let's suppose that we're dealing with the n equals 20 trials case again, but let's suppose that we observed 12 successes. All right, so we're not asking about the probability of 12 successes, we're asking what is the parameter that would have given us 12 successes, okay? And so what I want to do is I want to plot this function that we were looking at here on the right, on the previous slide. I want to plot this binomial distribution, but instead of it being a function of the possible x values, which are whole numbers, 0, 1, 2, 3, up to 20, I want to look at it as a function of the parameter values. These parameters are thetas that can range from 0 to 1. And so, oops, sorry about that. So on the next slide, I've got some code here that will accomplish this for us. So let's go back to RStudio, and we'll put that code in. All right, so the first line of code on line 6 here, I'm just telling R to build me a sequence of thetas going from 0 to 1 and by a very small increment. And then in the next, I tell it to plot the binomial function with theta as my variable. And I get a graph that looks like this. Okay, so what is this telling us? What this is telling us is, and we'll go back to the slide here for a little clearer picture of this. What this is telling us is the likelihood of observing those 12 successes over the range of possible values of theta. Remember, theta is a parameter that tells you the probability of success on any one trial. So you can't have a probability less than 0, and you can't have a probability greater than 1. So this is the entire range of possible values of theta. And you'll see that as theta gets closer to 0.6, the likelihood goes up. Okay? In fact, we can ask ourselves, what value of theta is the most likely given the data that we've observed? And you might guess that it is somewhere around 0.6. And you would be right. And we're going to show today how you actually compute that number, how you get that theta of 0.06. So this leads us to our topic of maximum likelihood estimation. It is a key problem in all of statistical inference that you want to be able to take a sample and then infer something about the population from that sample. It's like you're going up from sample to population, from data to parameters. And one solution to this problem, it's not the only one that we'll talk about this semester, but one very common solution is the notion of maximum likelihood estimation. Okay? Now, if you are one of those intrepid souls that likes to get more details than what the lecture says, I would invite you to read the following paper. All the information you would need is there. It's probably one of the most cited papers in the Journal of Mathematical Psychology, but it's Myung's tutorial on maximum likelihood estimation. It will go through everything that I'm talking about today in quite a bit of detail, and it's a great read. Be happy to discuss it with you at any time. We're going to do 3 examples today. But before we do those 3 examples, I want to kind of outline what the basic workflow of any one of these maximum likelihood estimation procedures is. So you can kind of think of it in 4 steps. Okay, the first step is you collect your data. Okay, so that's you do some research, you collect some data. Now you want to describe that data. You want a descriptive model for the data. So first we have to decide on a model for the data. And what we mean by that is decide on an underlying probability distribution. Is this data going to be binomial? Is this data going to be normal? There's another type of data that we'll deal with today called ex-Gaussian. There's all kinds of probability distributions that could serve as a model for the data. So we just need to look at our data and decide which one we're going to use. Once we've decided on that model, then the fun part. The fun part is step 3, where we define a likelihood function for that model, just like what we did with the binomial model a second ago. So we'll define the likelihood function, and then step 4, this is the actual estimation part, we find the parameter value, or values if there's more than one parameter, that will maximize that likelihood function. In other words, it will tell us what parameter gives us what parameter is most likely given the data that we've just seen. So collect data, decide on the model, define the likelihood, and then maximize the likelihood. That's the four-step process for maximum likelihood estimation. So today we're going to do 3 examples. The first example will be a binomial model, similar to what we've already talked about, but I'll show you how to implement all of that in R. The second will be a normal model, so we'll use a normal distribution as our model. And then finally, I'm going to introduce you to a new model called the ex-Gaussian model, which is going to be really good if you have a skewed distribution. So let's work on a first example. So this is going to be similar to what you've already thought about probably several times this semester. Suppose that in a sequence of 20 coin flips, we observe 12 successes. Okay, so remember, success we sometimes call, we've landed heads on 12 coins. So we got 12 successes. What is the maximum likelihood estimate for theta? Okay, so what value of theta is most likely given that we've just observed 12 successes? So step 1, collect the data. Well, that's done. I just told you we've observed 12 successes, so we can move on. Step 2, we want to choose a model. Well, given that this problem structurally looks like taking n independent trials and counting the number of successes on those trials, we can naturally think of this as a binomial model. So that's what we'll assume. We'll assume a binomial model. And a nice shorthand for that is this following notation. We say x is distributed as binomial with parameter theta and n set equal to 20. All right, so that says a lot of stuff in that little notation. But that little tilde that you see, that means is distributed as. So now we've chosen our binomial model. Now the meat of our likelihood estimation. Step 3 is to define the likelihood function. We need something to maximize, so we need to define it. Now this is a little technical note. You don't have to think about this too hard, but if you want to think about it, be happy to visit with you a bit more. What we're actually going to do is a little trick that works better. And what we're going to do is instead of defining the likelihood function, we're going to define the negative log likelihood function. Log refers to the logarithm. It's the it's the natural logarithm or base E logarithm that you might have studied in an algebra class. So we're going to define something that actually computes the negative log of the likelihood function. It's, again, not important right now to think about why that's the case, but it does work much better in computational contexts. So the way we do this is with a little bit of code. Again, I've provided all of these examples in the R script for this week, the week2.r, but I do want to walk through this a bit. So what I have to do is I have to define a function in R, and that's done in the following way. So I have a little thing here that names the function. This may look a little strange, but I call it NLL.binom. Now what that means is negative log likelihood, and then I just have a little dot for a visual separator, and then of course binom refers to binomial. So I know when I'm dealing in my R script with something, I know what the correct function is here. I know that NLL.binom, oh yeah, that's my negative log likelihood for the binomial distribution. So whatever the name is, I give it something that's descriptive. And so I type NLL.binom, and then I assign that as a function of 2 inputs. I'm going to be able to input some data and a parameter. So data and par are my 2 inputs for the function. And then everything contained within this brace and this brace is the actual computation part. And what I do is I return the negative log of the binomial density, where data is my input, the size is 20 for this context, and the probability is the parameter par. Okay? So that's why this works. Again, you can do this without thinking about it too much, but it's nice to know the structure of this likelihood function. So I'm going to copy all of that, and then I'm going to go put it over into R. Okay, put it right here, and I'm just going to execute it. Okay, so somewhere between lines 10, 11, and 12, I put my cursor, hit Command Enter, and that feeds it into R now. Now nothing has happened, but if you look in your environment, you'll see that there's now a function defined down there. So R knows it's there. Okay? We're going to do something with it in just a second. Okay, so we've completed step 3. Step 4 is the last step. Step 4 is we want to find the parameter that maximizes this likelihood function. Well, what we're actually going to do is, since we've defined the negative log likelihood, we're actually going to minimize that. Again, that's a technical note. We do that with the optim function. Optim stands for optimize. So optim is a one-line command. What it does is you feed it an initial parameter. We're going to set the initial parameter at 0.5. It's kind of a best guess for what will this be. You know, for a binomial model, just start in the middle, right? So we're gonna give a guess of 0.5, though I do invite you to play around with changing that initial parameter if you want. The next input to the optim function is the optimizing function. And what we're wanting to do is we're wanting to minimize this negative log likelihood function. So that's where I type in fn equals the name of my function, which is nll.binom. And then the last input to the optim function is the data. The data is that we observed 12 successes. And so I put in data equals 12. So again, let's copy all that, pass it into RStudio, and see what happens. There it is. I've got my cursor on that line. I'm going to hit Command Enter, and now I've got some stuff. In fact, I've even got a warning message. Don't worry. Let's just scroll up a little bit here. So everything you see here is the output of the optim function. It's actually a very verbose output. What I want to call your attention to is this first group up here, this $par. This is your optimized parameter. This is your maximum likelihood estimate. All right, pretty cool. This other stuff, it tells you what the actual negative log likelihood value was, how many iterations, and finally a 0 means it did converge. Technical notes that you don't need to mess with right now, but it is there. This is what you're worried about, okay? What you're worried about is what is my maximum likelihood estimate, and it is 0.6. Which of course kind of models the very first example that we did earlier. When you have 12 successes, the likelihood that's going to, the parameter that's going to be most likely for that data is 12 out of 20 or 60%. So the maximum likelihood estimate for this problem is 0.6. We are most likely to have an underlying theta of 0.6. Okay? So that's how maximum likelihood estimate works mechanically on a binomial example. Okay. The second example is going to be a bit more difficult, but the structure is going to be exactly the same. We're going to use the same 4 steps. We're going to define the likelihood function and do the optimization exactly the same. It's just the steps will be slightly different. So I've got a command down here, and I'm going to tell you the following command is going to load a data set into R, and it consists of 1,000 observations. And what I want you to do is to fit this data with a normal model and find the maximum likelihood estimates for those parameters, which are mean and standard deviation. Okay. So step 1 is to collect the data. And so again, this is in your R script, but I'm going to copy this and pass it into R. Oops. All right. I'll hit Command Enter. It's going to take a minute because it's kind of a big one. Let's see what happened here. Okay, it looks like I do have data. In fact, over in the console, I can make sure that I do have something that looks like it should. I'm going to say head of data. It's going to give me the first few lines of it. And you can see it's just some very, very long decimal numbers, 2.875, etc. But there's 1,000 of those things there. Okay, so that's the normal data. Let's go back to the slides. Now, before you start fitting a model, all right, if I say I'm telling you this is normal, let's actually make sure that it does look normal. So you can do that in 2 ways. You can do it with a histogram and with a density curve. So I'm going to show you both of these in R just real quickly. One thing that I can do is I can say hist data $x. Now what that does is, of course, hist means histogram. And then I'm telling R what to make a histogram of, and it's the data set data, but specifically the variable x, which I indicate with the $. So if I say hist data $x and pass that into the console, I get a nice graph. This is my histogram. You might wonder, is that normal? Well, it looks sort of symmetric, sort of normal. Okay, so maybe it's a good model. Another, and I would argue better type of visualization is what's called a density plot. And you can do that as follows. You can say plot density of data $x. Okay. So if we do that, we get actually a smoothed version of that histogram. And you can see there's a little bit of a wrinkle right here. So it's certainly not perfectly normal, but a normal model might be sufficient. It might be sufficiently descriptive. So let's see if we can guess what the mean and the standard deviation for this data is. That's what we're going to do maximum likelihood estimation for. Okay? So step 2 is to choose the model. We're going to assume a normal model. So we say that X is distributed as a normal model with parameters mu and sigma. These are the usual mean and standard deviation. Nothing new there. Step 3 is to define a likelihood function. So just like before, it's got a name, which I preface with NLL for negative log likelihood, but this time it's normal, so I'll say NLL.normal. You could call this NLL.Falkenberry, and it would be just fine. It really doesn't matter, but I like for the names to be descriptive. I'm going to assign that as a function of 2 inputs, the data, just as before, and a parameter set, just as before. Now, how does it work this time? Well, this time I'm going to return the negative sum of the log of the normal density. So that's what dnorm is. Normal density has data, mean, and standard deviation. Now there's something a little bit different here. Because this is a 2-parameter model, my parameters that I input are actually going to be 2-dimensional vectors. I'm going to have one parameter for the mean, so that's par 1 that you see. And then I'm going to have a second parameter for the standard deviation. That's the par 2. So this tells me put the first parameter in as the mean and put the second parameter in as the standard deviation. So I'm going to copy all of that, pass it over to RStudio. Okay. Once again, check my environment. I can see I now have the NLL.normal function in there, so that's good. We'll go back to plots here in a second. And then the third step, of course, is going to, the fourth step is going to be, let's find the parameters, mean and standard deviation, mu and sigma, that maximize the likelihood function. So again, I do this with the optim function. Optim has 3 inputs. I input the initial parameters, which I put in this way. I say that my initial parameter needs to be a vector where the first parameter is 1, and the second parameter is 0.1. So this is like an initial guess at the mean and the standard deviation. Okay? The function that I'm going to minimize, or maximize if you will, is the NLL.normal function that I just defined. And finally, the data is going to be, well, it's those 1,000 observations. So it's data $x. Okay? So I'm going to pass all of that into RStudio. All right. And let's do a command enter. Warnings right now. Let's go up and take a look. So here you can see our output. Our output now is 2 numbers, these par values. The first one is 2.8494, etc. And the second one is 0.1214, etc. What are these? Well, this first one is the mean, and this second one is the standard deviation. All right, pretty cool. Once again, I'll show you, just so you have this on your PDF as well. You can see these are the 2 parameters. These are the maximum likelihood estimates for the mean and standard deviation. Now, a good thing to do is to see how well our model fits the data. So I've got 3 lines of code here that will help you do that. Let's go back over to RStudio, put those things in, and let's execute these 3 guys right here. Oops, I got something wrong here. I messed up, guys, and I'm not sure why. Error in the plot, figure margins too large. Let's move this up just a little bit and see what we can do. There we go. I didn't have enough room down there is what happened. Okay, so you can see right here the original curve was the wrinkly one, right? That's the dark line. And then the normal curve that we just fit has mean of, I believe it was, let's go back up here, the mean was 2.849. You can see I've rounded that to 2.85 in my normal density, and I rounded the standard deviation to 0.12. And you can see that's a pretty darn good fit. Other than that little wrinkle right there, you've got a very nice bit of overlap between the data and the fitted model. So that's a really nice way to find a good description of your entire data set, not just the mean. So that's pretty nice. Okay. Let's go back and now do our third example. And our third example is going to be similar to the second, but a little bit different at the same time. So here I have you a set of 1,000 response times. If you know anything about my research, you know I deal a lot with response times. And those things tend to look very interesting. All right, so I've got a command here and a plotting of a density curve that we'll put into RStudio. Scroll up on this just a little bit for you. All right, so let's read some data in real quick. So again, this is 1,000 different data points. All right, let's take a look at what the data looks like. We'll just do the head of data. And you'll see that it has a column that's called RT, and these RTs are in seconds. So 0.984 seconds, 1.373 seconds, etc. There's 1,000 of them there. Let's plot the density of those things, and you can see we have something that no longer looks normal. It's no longer symmetric about the peak, and this has, remember, this is something that has a positive skew. So how are we going to fit that? Are we going to be able to fit it with a normal model? Well, we probably shouldn't, right? Because it's certainly not normal. It has skew to it. So what can we fit it with? Well, that's something new for us. What we're going to do is we're going to fit it with something that's good for modeling these things. And that thing is an ex-Gaussian distribution. There's a little, you can see I've referenced a paper that was written in the late 80s here. You can take a look at that. You can see this has been around for a while, this notion of fitting reaction time distributions with ex-Gaussians. But in a nutshell, an ex-Gaussian distribution is essentially a combination of two things. A Gaussian distribution, which you're used to, as well as what's called an exponential distribution. When you stick them together, you get something that looks like that curve we just looked at. You've got a normal component and an exponential component. Oops. So let's see if we can figure out how to do this fitting. So we're going to fit the RTs as an ex-Gaussian. An ex-Gaussian distribution has three parameters. It has mu, sigma, and tau. Mu and sigma are exactly what you think they are. They're mean and standard deviation of the normal part, but then tau is the part that represents the exponential component. Now there's one small problem. The ex-Gaussian distribution is not already in R. You have to build it yourselves, okay? So again, the week 2 script has this already in. Don't try to type all this stuff from scratch. You'll just hopelessly miss a parenthesis somewhere. I have triple checked this one, so I'm pretty confident that it works. At least it empirically works every time I try it. All right, let me go back to RStudio. We'll put all that stuff in, and then we'll pass it into the console, and so now you can see in the environment we now have a DEXG, that's density for ex-Gaussian. That's going to help us here in just a second. All right. Having trouble switching back to my presentation here. So that's step 2. Step 3 is to define the likelihood function. So just like before, we have NLL as the prefix. It's telling us this is a negative log likelihood. EXG for ex-Gaussian. This is a function of data and parameters, just like before. But this time I have 3 parameters. All right. So I'm going to return the negative sum of the log of that ex-Gaussian density, where I put in the data, and then the 3 parameters: mu, which is the first parameter, sigma, which is the second parameter, and tau, which is the third parameter. Again, copy all this stuff. Don't try to type it from scratch. And that will, once we put that in and pass that to the console, oops, start up here. There we go. Now we've got our negative log likelihood function. Okay. Last step, step 4, is to find the parameters that maximize it. So we again use the optim function. And so just for quick, I'm going to copy that, put it over into RStudio. Notice this time the par, the PAR part, these are, again, the initial guesses. I'm guessing a mu of 0, a sigma of 0.1, and a tau of 0.1. The fn, the function that I'm minimizing, is nll.xg, and then the data is this data $RT. So once again, let's pass that into the console. And let's go up here and look. And you can see now that our output is 3 parameters. And again, these are mu, sigma, and tau, respectively. So let's, just like before, let's put that in as a sort of a sanity check, if you will. Does this actually fit that distribution? So got all that stuff there that we can copy in. Oops, once again, I've got my space too small, so let me pull that plot up just a little bit and try this again. And you can see this is an exceptionally good fit. In fact, that's so good, I want to just blow that up a little bit so that we can see it. It's not perfect, obviously. I mean, the dashed line is the ex-Gaussian curve. The dark line is the actual data. But you can see that follows that data really nicely and gives us a nice 3-parameter solution to that curve. Fitting it with a normal would not be anywhere nearly as good. And in fact, you'll discover that in your homework this week. Okay, so let's go back to the presentation. I think we're just about done. Yes, that's the last slide. So just as a recap, the whole idea is we're doing maximum likelihood estimation. That means we're estimating parameters that describe distributions for us. So you get some data, you want to find what's the parameter or parameters that maximize, that are the most likely given the data that we've seen. And the way we do that is we define the likelihood function, and then we do an optimization routine on that. So if you kind of understand what's going on conceptually there, work around with R with some examples, and you'll kind of get a feel of how this stuff is done. It looks like a lot of really intimidating code, but there's an inherent pattern to it that if you do it enough, I think you'll really get the hang of. So the best way to do it is to just do it. I've given you a homework assignment with 4 or 5 exercises that will be similar to these, but will ask you to go just a bit further than what we've done in the lecture. As always, make sure that if you don't understand something, that you ask questions about it. This is not easy material, but it is very rewarding once you get to it. So if you have any questions, let me know, and if not, then I'll see you in week 3.